Hi class, welcome to nuclear chemistry. This is our first time trying this method for taking notes and copying along, so bear with me please. What you want to make sure you have out is your reference table, and if you are taking notes on paper, make sure you have a copy of the note packet that was sent to you. If you're going to be using this on Cami and taking the notes, either have it open on a separate window, or if you want to just be able to go back and fill them in later, just follow along and see how you can do. The copy of the PowerPoint or the slideshow will also be in Classroom as well as this video, so you can always go back and look at material. So what you want to look at is, we're talking about nuclear chemistry. Now, nuclear chemistry, of course, is talking about what's inside the nucleus, the inside the atom. Very different from our others. This overview here is what we're covering today. It may seem like a lot, but many of the concepts here tie into one another, and they'll go very quickly. There's a pattern that you'll start to notice here. So we're going to talk about what makes an atom stable, defining the different types of reactions, and then identifying them, comparing the different emissions that are given off, and then being able to write chemical equations. Those are the objectives that I hope you'll be able to do by the end of this lesson. At any point, of course, you can pause the video, you can come back and watch it again, slow it down, speed it up, totally up to you. All right, first thing you want to do is make sure you go back and review Unit 2, the different parts of the atom. I'm going to go through this quickly because I assume you did that already last week. We have your protons. You can go back and look at Rutherford's experiment. So again, when you open up the slide, you can click on these different links and it takes you to videos if you'd like. We talked about what isotopes are, atomic number, different masses, the symbols and the notations we have for writing nuclear particles and isotopes. Right. Here's a good place to check yourself. So pause the video here, fill in your notes, make sure you can answer these questions and fill them in. This is your preview review. Okay, after you're done, you can check your answers. And again, pause the video anytime you need to check your work. Different chemical reactions we've talked about over the course of this year so far. We talked about the also physical changes that you have. It's all about the electrons when you're doing chemical reactions. Either they're being transferred in ionics or they're being shared in covalent reactions. With nuclear reactions, we're talking about the nucleus. New elements are going to be formed. You are looking at two different things to start with and end with. So it's not a matter of balancing out the right elements. You're actually looking for brand new elements being formed. Again, you're changing the nucleus, so you're changing what element you're dealing with. So here's a quick check for yourself. Which one below represents a nuclear reaction? Okay. What is nuclear chemistry? Well, of course, it's the study of the nucleus and its reactions and different energy that comes from that. There are 4 types of nuclear reactions, and we'll go through each one of these and be able to identify them, talk about what's happening within them, how they're similar and how they're also very different from one another. Again, you're going to need your reference tables out. You'll need table N, and here's a blown up view of what table N looks like. And this symbol right here, you're going to use table O if you need help to figure out what that symbol is. It's called a beta particle for the carbon-14. So over here, you're told what the nuclide is called, its half-life, the decay mode, and the nuclide name. The nuclide name, carbon-14, could also be written with a 14 in the upper left-hand corner again. That's back from Unit 2 if you want to go back and review your atomic structure. All right. So what makes a nucleus stable is important to discuss first. It's all about the proton and neutron ratio. For your lighter elements, you want to have about a 1-to-1 ratio of protons to neutrons. This is a guideline, and it's for elements that are considered lighter or atomic number 30 and below. So look at zinc and below, and you want a 1-to-1 ratio. Heavier elements above 60 need about a 1 to 1.5, and then it goes on from there, in between. They need more neutrons. So when you have a stable nucleus like carbon-12, nitrogen-14, oxygen-16, you can clearly see the ratio of protons here. 6 protons, another 6 gives you the mass of 12. Nitrogen's also stable. Again, these are guidelines. It's a generalization here, but it's a quick, easy prediction to see whether or not your nucleus is stable. I kind of think of this as like children in the backseat of a car. If you have too many squished inside each other or inside that space, you're going to have to put a buffer in between them so that they're not fighting. And those neutrons kind of act as those buffers. So the more protons you stick in there, the more neutrons you're going to need to keep the positives from seeing one another and repelling and kicking each other out of that space, the nucleus. Unstable nuclei don't have that 1-to-1 ratio, so carbon-14 here. When an isotope is not stable, it means the nucleus is going to decay or transmutate, to change, naturally, all on its own. Nothing else happens to it. It just does it. This is a diagram you might see called a band of stability. And you can see when the elements, their isotopes, fall within this range. Right here, it makes a stable isotope. So these are your stable isotopes, and the ones that fall outside of that range are considered unstable and radioactive. Again, it's a prediction. There are 4 types of nuclear reactions, just like we had chemical reactions, and we can break them down into different ways. These 4 nuclear ones we can also talk about. It helps us, again, predict what they're going to make if we can identify what type of reaction it is. Natural transmutations are the ones that happen spontaneously. These are the elements that you find on table N. They're going to change from one element into another to make themselves more stable. So table N just gives you an example of some of the radioactive isotopes or radioisotopes. They can give off a beta, an alpha, a positron to make them decay into something more stable. Again, those particles you see on table O. And here's an example of one. So your uranium turned into a thorium, and it gave off this He, helium, or alpha particle. Artificial transmutation is the next type. It's when you have one nucleus changing into a new one, but you're forcing it to happen, usually by bombarding it with a particle. Again, you can use an alpha, beta, positron, neutron. They're also called bombardment, alpha bombardment, and it changes it into a new one. So natural transmutation happens on its own. Artificial is being forced to happen. So here you can see a nitrogen is turning into an oxygen. Now, the way they write this symbol, it's hard to tell if they're talking about the element helium or this alpha particle here. We'll get to that a little bit more, don't worry. The third one we're going to talk about is fission. It's when you have a large nucleus like uranium and plutonium, and you're hitting it with a neutron. It splits into 2 smaller nuclei. So to fission means to split. So you're taking this uranium. Now, luckily, only specific isotopes do this, uranium and plutonium. It doesn't usually happen naturally, but you can find some natural examples of uranium doing this. We won't worry about those just yet. And the last one is the fusion. Fuse, again, means to bring together. So it's when you take 2 small nuclei, like hydrogen, fuse them together, and they make themselves into one helium. So the protons merge together to make a new element. And here's an example of that happening, where the 2 particles are coming together and turning into a helium, and they also happen to kick out a neutron in the process. All right, so here are 4 different reactions, the ones that we just went over. Take a look and make sure you can identify what they are for types of nuclear reactions. And here's a quick check for yourself. Now we're going to talk about each one of those reactions in a little bit more detail. The natural transmutations are when you have a nucleus of a radioactive isotope, an element that's radioactive, spontaneously giving off a particle like an alpha, beta, or a positron, again, table O, and turning it into a new element. Reference table N has many of the decay modes already written out, so if you're asked to write a reaction or to tell what the particles are going to be, you'll need to use table N to figure that out. So uranium-238 is changing into a thorium-234, and it's giving off an alpha particle. In the process, they sometimes give off an energy. And again, that giving off of energy, that breaking down into something new, is what creates something being more stable. You might recognize that as being an exothermic reaction. Okay. There are 4 particles commonly given off with your natural transmutation. Again, you're going to find all of these symbols on table O. The number on top is our mass. The number on the bottom is either called your nuclear charge or your atomic charge. Sometimes we just call it charge because this is the nuclear unit. It's all about the nucleus. The alpha symbol can be written in 2 different ways. The beta symbol can be written either way. Same with the positron. Now, positron is like a positively charged electron. Notice that the nuclear charge of it is +1, but it has a 0 mass. We'll talk about those in a bit. Now, these 4 particles, as they're given off, we talk about how they can harm body tissue. The alpha particles have the lowest damaging ability when they're outside the body because they're blocked by paper or your dead skin cells. Unfortunately, they're the ones that are more dangerous inside of your cells because they are so large. Your beta particles have a medium harmfulness. They're blocked by cardboard and wood. Same with your positrons. Now, the beta is a really interesting particle. If you think of think of a neutron as like a proton and a neutron that got stuck together. That's what gives it the mass of 1, but a positive charge. As you get rid of, proton and electron stuck together. As you get rid of the positiveness to it, the negative stays behind, attaches itself to another proton, turning into a neutron. Don't really worry about that so much. We'll do some math and you'll see how it works, but it's kind of a cool particle to think about. Positrons, again, are like a positively charged electron. Again, neutrons inside the nucleus have multiple things that they can break down into. It really all has to do with the subatomic particles that are inside of the protons, neutrons, the quarks. Your gamma radiation is just an extremely harmful amount of energy. It can only be blocked by lead sheets. If you think of it kind of along the lines of X-rays. And this is almost always given off with the reactions. We don't have to worry about writing them in an equation because the mass doesn't change and the charge does not change here either. At the bottom here, you're going to find little videos once in a while that you can check if you go back to the slides and watch on your own time. Here's just some diagrams that show how those different particles are affecting the body, what they can go through. And then down here is a picture you might remember seeing from Unit 2 as well about how we use protons, neutrons, and electrons here, but talking about how positives are attracted to the negative, negatives are attracted to a positive magnetic field, and things that are neutral are not affected at all. So one of the things you'll be able to do at this point is to complete nuclear reactions. You can fill in the missing particles by using the conservation of mass and conservation of nuclear charge. So again, the number on top is our mass number. The one on the bottom is the nuclear charge. So I'll walk you through the first one in my thought process. All right, I look at the mass. I have 207 on the left. The arrow is like the equal sign. The positron there has a 0 already written in, and I'm trying to figure out what that number is. For the bottom number, I'm looking at the 84. There's my equal sign. My positron has a +1, so I have to figure out what that bottom number is as well. So the number on top is 207, and mathematically that number on the bottom needs to be 83. Now I just look at my periodic table to find out what element number 83 is, atomic number. Don't worry about the mass because they're different isotopes, but 83 matches with bismuth, Bi. All right, at this point, you're going to be using a lot of those elements down in those lanthanide and actinide series down at the bottom of the reference table, of the periodic table. All right, for the next one, we have a plutonium-239. Now, this one's the next step of difficulty. You notice that there are 2 pieces missing. So you're going to have to do a little bit more. First thing you want to do is check table N and see if there is a decay mode for the plutonium. And of course, there will be. So the first thing we find out is it gives off an alpha particle. It's really helpful to write it with the 4/2. You can use the alpha symbol here or the HE, it doesn't matter. But by writing that 4 and 2, it allows you to do the math easier. So again, we want to look at the masses being conserved. So the left side of the equation has to balance with the right side. And then I have to do the same with the nuclear charge. So on the top, I end up getting, 235 on the top and 92 on the bottom. And again, you look at your periodic table to find out what element symbol matches that 92. Every one of these nuclear reactions are going to be done the exact same way. You make sure your nuclear charge is conserved, and you make sure your nuclear mass is conserved. So the numbers on the top are your mass, the numbers on the bottom of the charge. Table O helps you figure out what to put in for those particles. Your periodic table helps you figure out what elements, and occasionally you'll have to use table N to find the decay mode, figure out what that particle is that it's giving off. Go ahead and try the other 3, and then you can check your answers. I don't have them up here right now. You have to do that on your own. All right. Now, if we want to take this to the most difficult way to write these questions, they're going to be word equations, where it just says simply write the decay equation for potassium-42. You want to start off by writing your nuclear symbol in a more useful way, putting the 42 on top, the K, and now I'm going to have to look up that atomic number or the nuclear charge on the periodic table. So take a minute, pause the video, see how much you can get done of that, and then check your answer here. So I've got 42 over 19. I looked at table N, found out that it was a beta decayer, which means it has a 0 and a -1. The 42 is the number on top, and the 20 is on the bottom. The next question is, what isotope can you create when neon-19 decays? And again, you're going to need to use table N and table O possibly. Pause the video, take a minute to check it. All right, Now, occasionally you're going to find some elements like this uranium-238 that it decays, and then that product decays. This is sometimes called the daughter product. This is the parent, and then you have a daughter product. That's going to decay, and then it keeps going because the whole idea is you want to get to a stable element. The last stable element is lead on the periodic table. So every element heavier than lead is going to go through a series of decays. It's just a cool thing to look at. It may show up in your future studies. We're going to pass through that pretty quickly. Question is an artificial transmutation. Again, these are the ones that don't happen spontaneously. You need to get them started by doing something to these particles, to these elements. So you might be working with a stable nucleus like nitrogen-14. You could be working with a radioactive one. It does not matter. The idea is that you're going to take one nucleus, bombard it or hit it with a particle, and it will cause the nucleus to change into a new isotope, a different element. Extra particles are sometimes also produced as a byproduct. So you'll see in this reaction, this helium or alpha particle is zooming, hitting into that nitrogen. It gets stuck inside the nucleus and causes it to break apart and spit out a proton in the process, or hydrogen. When you're answering these questions, you're going to fill in the pieces the same way as before. Pretend that there's an eye there. All right, so when you're looking at this equation, we have nitrogen-14. It's being bombarded with the alpha particle, and we're going to find the missing piece right here. And through the magic of video, I just have this oxygen being amazing. So I have 7 and a 2. That again adds up to 9. So when I look over here, I already had a 1 from that proton being formed. And then that's going to have to be an 8 to give me 9 on the bottom. On the top, I have 18. Therefore, I know that I need to put in a 17 to match that up with that 1 to get back to the 18. It's all about the conservation of mass. So we don't spend a lot of time going over each one of these individual examples because they're all done the same way. Honestly, the hardest part is remembering to put in the mass and the charge when it's not shown. Make sure you use your periodic table to find the 13. Make sure you're using your table O to find the missing pieces. If there are ever 2 things you have to find, well, then there'll be table N to look at to find the decay mode. I just wanted to point out these 2 reactions. Rutherford was the first one that did the artificial transmutations, and then Irene Curie did the second one where she was able to create the first radioactive isotope. And this gives us important stuff to work with later and talk about how you can create new elements that you're looking for. With this phosphor, it happens to be a natural decay, a positron decayer, as it's shown in this next example. So again, you can fill in these missing pieces and then check your answers. All right, moving forward, we're going to talk about fission and fusion. Just a quick overview, and you don't need to write this stuff down just now. But Einstein had talked about E equals mc squared, where before this, we talked about how energy and matter are always conserved in chemical reactions. Well, with nuclear reactions, there's a conservation, but that matter is changed into energy. So we still have the mass numbers conserved and the atomic number conserved, but now when we're talking about the overall energy reaction of the reaction, it's not going to be the same masses. There's a tiny bit of mass that's converted in this process, or that seems to be lost, and it's turned into an energy. It's called the mass defect. This is really a huge, heavy component in here. It's really going to be talked about more in physics, hopefully. And if you go in to be a nuclear chemist or nuclear physicist, well, then you'll definitely need this. But it's kind of the ooh-ah of where our energy comes from in the nuclear reactions when we have fission and fusion and how we can use these for energy sources. Okay, with your fission reactions, it's the splitting of a heavier nucleus, usually uranium and plutonium. Those are right now the only elements that we know will work with fission. And it produces 2 lighter nuclei, 2 new elements, about equal in size usually. You need to start a neutron with this. The neutron gets into the nucleus of that uranium, and it essentially splits it open into 2 elements. In the process, again, a little bit of mass is lost, turned into energy, like huge amounts of energy. These are commonly used in our power plants and nuclear weapons. The new element created from the fission is always radioactive. And because that neutron hits that uranium, splits it into 2 new pieces, we sometimes don't know what those new pieces are going to be. It could be a barium, And again, we can use our conservation of mass and charge to figure out what that other species is that's going to be in that space. Make sure the mass is the same on the top. Make sure the atomic number is the same on the bottom. This one's a little trickier because that has 3 neutrons that it's making. We're going to talk about that in just a moment. Okay, so you can go ahead and figure out what that missing piece is. All right, there's a fun video here if you want to watch that. All right, so it was the Krypton 92 is what it did make in that one. And again, the products that you're making here are always radioactive, which means that they're going to go through their natural transmutation. So that barium then turns into the lanthanum, it gives off a beta. That element then turns into cerium. That element then turns into promethium. All the while, it's creating all these radioactive particles and giving off these emissions along the way. We talked about how beta and positrons are harmful. They're harmful to body tissue. The krypton does the same thing. It turns into rubidium, which goes to strontium, which goes to yttrium, which goes to zirconium, and then you finally get your stable isotope. So again, it's giving off all these different radiation particles along the way. This lies the major problem with using fission reactions. We'll get into that more. The fission reactions are also these chain reactions, which are really cool to watch. You see how that neutron hits that uranium, splits into 3 more neutrons, and those neutrons are available to hit more uraniums. They split, produce more neutrons. Those neutrons can go and hit more elements as well. So it's the good and the bad. Okay, so one single neutron produces 3 more, and then you get your chain reaction. Right. Nuclear reactors work on this premise, on this idea that you can continually create more energy. You need to have moderators to slow down those neutrons, and then there's control rods that absorb extras. We're not going to go into the details of how nuclear reactors work. If I had more time, I would love to. This is truly amazing science that happens in here. Again, the main idea is that you have a small amount of mass that seems to be lost. It doesn't show up in our equation, but it shows up in the real world. And you can use the E equals MC squared to figure out how much energy. It's kind of neat. Chain reaction that happens, if it's controlled, we have nuclear power. If it's not controlled, we have an atomic bomb, which is why the problem can be with nuclear reactors. If they do go out of control, they're basically a nuclear bomb waiting to happen. You'll always see these cool cooling towers on your nuclear reactors. That's just steam coming out. It's just water vapor. That stuff is not harmful at all. There's some cool things in here that talk about where the nuclear reactors are in the United States, how nuclear reactors work, the reaction issue that they had in Japan when they had the accident. It was a few years ago now. So there's really some nice information, some cool information, really, really neat stuff to look at when you have the time. And the different types of nuclear reactors, again, we don't need to get into that, but it's there if you want to look at them. Where the first major accident happened in Ukraine, at Chernobyl, and some other stuff with this. Again, it's a really cool tie-in with your history class. Hopefully you talked about that. We talk about the nuclear bombs as well, how much mass you had in here, 4 kilograms of uranium. That's it. That's all you needed was 4 kilograms of uranium to create that destruction. All right. Now the fusion reactions, these are the ones where you take a light nucleus, you bring them together, and it turns into one heavier one. Generally speaking, we're talking about hydrogen fusing to make helium, and this is the reaction that takes place on the sun, creating huge amount of energy. Thank goodness, we kind of need that energy. Again, these reactions are done the exact same way. You're taking the mass on the top, you're looking at the number on the bottom to find the missing species. That's all you need to do. When you're given a symbol like this, you want to make sure you use your atomic number from the periodic table or table O if it happens to be a particle. Things like the helium and the hydrogen are atomic symbols, and they're also nuclear symbols. So it's an element and it's also a species. It doesn't matter which one you use to get the answer. With that first one, when you go this, you're going to have a 0 up on the top here because that's a positron. So the number on the top has to be 2. That's a 1. That's a 1. That's already a 1. That's going to be a 1 down here. So you've just turned this into a hydrogen with a mass of 2, which is called a deuterium, by the way. If you had a hydrogen with a mass of 3, it's called a tritium. Anybody who's a fan of some Marvel comics, I believe it's Spider-Man that talks about tritium. You'll hear about heavy water using deuterium. So the problem with the fusion reactions is that it takes a really high pressure and high temperature in order to force those nuclei to come close enough together to overcome those repulsive forces. And it's just not really a practical thing to do here on Earth just yet. The good thing about fusion is that it doesn't create those byproducts like the fission does. So you get just as much energy, but you don't have the harmful radiation of those alpha and beta particles being given off. So there's some extra information here that you can look on how the sun works, where the energies come from, if you're interested in all of that. So quick overview, can you identify the different types of nuclear reactions? These are all nuclear. That should be pretty obvious by now. And you want to be able to identify if it's a fusion, fission, natural transmutation, or artificial. Now, many people will say that fusion and fission are also artificial, but I'd like you to be able to identify them more specifically. If you've picked it out as being a natural transmutation, specify what type of natural transmutation. Is it a positron, a beta, an alpha? What is the decay mode? Just to get a little bit more, a better answer for these questions. Okay, and if you just click through, you can check your answers with what's up there. Okay, that's it for today. Tomorrow or next class, we'll come back and cover a little bit more. Again, you can watch this video as many times as you need to. You should be filling in your note packet, and your assessment of this is going to be how well you do on that worksheet for the reactions. There are some things in the objectives that I won't be able to really check on right now, so we're just going to worry about those at the end when I do like an end of the unit review. So for now, I'm looking at basically, can you write those reactions? Can you figure out how to do the particles that are being created? And can you compare the different reactions? That's, again, essentially, if you again look back at the objectives for today, that's what I want to make sure you're able to get from this video. Let me know what you thought of this. Again, you can speed it up, you can slow it down, you can watch it again. Thanks very much. Have a good day, guys.